Okay, so I guess we can start. Good afternoon, everyone. My name is Avi Tzadok. I'm from the Faculty of Engineering of Bar-Ilan University, and I'm very pleased with this opportunity to speak with you in the next 45 minutes or so about a certain type of optical fiber sensors. And in this presentation, I will touch upon a few things we do in my group, but most of the things I show you are based on the works of others, and I will try to give the credit for those others whenever relevant. So this presentation is meant for you if you know something about optical scattering processes, not necessarily a lot, but you have some background, and you know a few things maybe about optical fibers, but you are not necessarily specialists in these fiber sensors that we're going to talk about. If you are specialists, then I apologize in advance, then perhaps this is not the right webinar for you. I will probably not reach your level of expertise, but I will try to address these issues to those who are not specialists, but want to learn a few things about these fiber sensors. In the outline, I will start with very briefly touching on optical fibers, what these are and what we do with them. And then most of the talk will be dedicated to two specific processes that we use in sensors. They are called collectively Brillowin scattering processes, and they come in two flavors, in the backward direction and in the forward direction. And we'll speak of the physical principles of those and how we use them for sensing and what we can and cannot do using these phenomena. And I will be glad to take your questions, but if possible, I prefer that we keep them till the end. You can communicate your questions to me via the Q&A module of the Zoom platform. If there's something absolutely essential, then please stop me along the way. If not, I will try to reach these questions when we finish. So fibers, optical fibers, in order to appreciate them, then maybe I can compare them to something that we all know and like, spaghetti. And you'll find that fibers are thinner than spaghetti in their dimensions. They're cheaper per unit length. If you actually check how much spaghetti is in a package and how much it costs, then a fiber is going to be way cheaper per meter or kilometer. The demand per spaghetti and fiber is actually comparable. If you check in the US, how many kilometers of fiber are installed and how many kilometers of spaghetti people eat, it's actually on the same scale, even though I would not necessarily recommend that you taste spaghetti. And optical fibers enable our internet communication. You can say that fibers make our world go round these days. And this is ever more present in these days of coronavirus, when we all rely on these remote platforms for every sort of interaction, but even before that. And how good are these fibers? We can relay as much as 50,000 gigabits per second over 10,000 kilometers, that is across the Pacific, using just one optical fiber. And compared to any other platform we had before that for massive communication, this is 100 times longer reach and maybe 5 orders of magnitude broader bandwidth than we could ever do otherwise. So fibers changed our world. And this nice boy here is not my son. He could be my son a few years ago. And I guess that these scenes are repeating in many homes around the country and around the world when we are finding it difficult to draw our young ones away from the screens and from the internet. And this is the making of fibers. And this is the doing of fibers. And if you maybe do not have children in these ages and you may not relate, perhaps you can relate more to these situations. And fibers certainly affected many aspects of our lives, most aspects of our lives. And the society task of people like me or researchers working on optical fibers, I sometimes explain that as we are the plumbers of internet. If previously only these guys were the plumbers, and of course, we all say no to crack. Today, this nice gentleman here with the glasses and all is also a plumber. Only he's plumber of information, not water. And obviously, we cannot survive too long without the guy on the left when we have problems with water flow in our homes. We can also not survive too long without internet connectivity. So this plumbing is becoming more and more essential to our society, to our economy, to our lives as a whole. So optical fibers matter, and the inventor or foreseer of optical fibers, Charles Cow, was awarded the Nobel Prize in Physics in 2009 for this invention. And the citation of the Nobel Prize reads for groundbreaking achievements concerning the transmission of light in fibers for optical communication. And interestingly enough, Charles Cow did not write a patent on this invention because he said he wanted to give the optical fiber to the world. This is something for many of us in academia to think about. So, I told you a bit about fibers in communication, but this is not what is the subject of this particular seminar. We're going to speak about sensors. And fibers are excellent sensors for measuring things. Why? Of course, they're long. We spoke about reach. We can use fibers to take measurements over hundreds of kilometers if necessary. They are very thin. We mentioned that as well. So we can embed optical fibers in many structures with simplicity and with little effect on the functionality of these structures. They are suitable for hazardous environment, such as gas tanks, oil wells, pipelines, where we may not wish to use electricity, voltages, currents. And the propagation of light in the fiber is affected by many conditions and many variables that we might be interested in measuring, such as temperature, mechanical deformation, stress, strain, sound, vibration, the presence of electrical and magnetic fields, chemicals, biological reagents, and so on and so forth, which means we can measure many things rather conveniently. And today's focus will be on a specific family of effects or specific propagation effect in optical fibers, which is very useful for sensing applications. Is this the only one? No. Optical fiber sensors are around for over 40 years, and various physical principles are being employed towards optical fiber sensors. It is not possible to cover all of them in a single presentation. So this is definitely not a complete discussion of what can be done. I'm just going to focus on this particular effect because I think it's interesting from the physics point of view, and it has a very broad and sometimes surprising range of applications. And it is also what we do in parts of my lab, which is of a personal interest. The effect is called stimulated Brillouin scattering, or SBS. I will explain what this is. So there will be two main parts, and the first one will speak of an effect between waves that are counter-propagating in opposite direction. This is what it is called Brillouin stimulated, SBS. So let me try to illustrate this. In this effect, we send two optical waves along the same fiber. The first of them is called a pump, and that pump wave is propagating in one direction along the fiber, I just illustrated. And sorry. If we wish to describe that wave technically, then we will speak of a magnitude, we call it A pump. We'll speak of optical frequency, omega pump, a wave number. Wave number is how many spatial periods there are. It's the inverse of wavelength. We call this K pump. And this disturbance is propagating from right to left in the negative Z direction along the fiber. Now, one wave is not enough to generate the effects that we're interested in. We need at least another one. And the second one we call a signal. that signal wave is counter-propagating. It is propagating in the opposite direction. It has its own magnitude, A signal, its own frequency, omega signal, and wave number, K signal. And it is propagating in the positive direction along the same fiber, so the opposite direction. Now, when these two exist together, they generate a beating pattern. Why is that so? When we speak of optical power, optical intensity, it is the magnitude of the field squared. So when we have two waves like this, we add them together, and the overall magnitude is pump plus signal squared. And this intensity pattern, if the two waves were, say, the same frequency, what we could expect is a standing wave, like we've seen many times in our studies. But this case is slightly different because frequency of pump and frequency of signal are not exactly the same. They are detuned. Therefore, this overall intensity that I tried to show is not stationary, it is moving. It is moving in the direction of the pump. And what can we say about it? This intensity is itself a pattern with a frequency. It is described by the difference between pump frequency and signal frequency. And it also has a spatial period, and it is the sum of K pump and K signal. Now, these frequencies are comparable. Therefore, we can approximate the sum of these two wave numbers to be twice K pump, and we'll call that Q for what is to come. So if I look at this intensity, optical intensity, it has a magnitude proportional to this product, A pump conjugate of A signal, and, a frequency that is the difference between the two, and the wave number that is the sum of the two. So how are we using this? We rely in this effect on a very specific property that optical intensity can drive mechanical waves or acoustic waves. Now, this comes like somewhat of a surprise initially, at least it did to me, because in our studies in first year of physics, of engineering, we are told about mechanics in the fall semester, and we are told about electromagnetism in the spring semester, and we are accustomed to think of these two physical phenomena as separate entities. But this is not fully correct because physics is not divided into compartments so easily. And the fact of the matter is that electromagnetic intensity does exert a force, a mechanical force, in the Newton sense of the way, of the term. So electromagnetic intensity can drive mechanical motion. It can drive the oscillation of mechanical waves or acoustic waves. And more specifically, the mechanical force scales with a gradient, with a spatial gradient of intensity. And that intensity pattern that I showed you is not fixed. It is changing along the fiber with a certain period. It is also changing across the fiber because all these optical waves are confined to the fiber core. So let us examine the scale of these profiles. When we go along the axis, if you recall, the wave number is twice the optical wave number. This means it is very, very large. It means that the spatial period is half the optical wavelength, something on the order of half a micron, 500 nanometers. Therefore, the intensity that exists in the fiber, this beating term, is changing on a very, very short scale of a half a micron. That goes to say that this gradient in intensity is very, very large. This intensity is changing across such a short scale. Therefore, we can expect a very strong mechanical force in the axial direction, in the direction of propagation. In comparison, when we look at the transverse direction, the cross-section of the fiber, changes happen more slowly because the electromagnetic energy is confined to a core that is 4 or 5 microns in radius. That is a scale that is larger, 10 times larger than the axial variation. Therefore, gradients in the transverse plane will be comparatively smaller. Altogether, this goes to say that our two optical waves, the pump and a signal, give rise to mechanical force that is pointing along the fiber axis in the direction of propagation. Therefore, that sort of mechanical force can excite only specific sorts of elastic waves. The waves that can come into action here are those that propagate in the longitudinal direction, because this is the direction of the force. They have to acquire the frequency of that force, that is difference between pump and signal, and they have to acquire the spatial period, the wave number of the driving force, that is Q. So we are looking to find these exact sorts of acoustic waves because these are the ones we can simulate, or these are the ones we can generate with light along the fiber. And in order to illustrate these modes and find them, I'm using a diagram that we use often in nonlinear optics and optics in general. It is called the omega K diagram, or dispersion relations. And what I'm plotting here on the vertical axis is frequency omega, and on the horizontal axis, it is wave number, axial wave number in the direction of propagation. And every sort of wave, every mode in a structure, optical wave or elastic wave, is characterized by the relation between omega and K. This is what we call a dispersion relation. And I've drawn here the optical mode in a fiber. It can propagate in one direction or in the other. And I've plotted for you also an acoustic mode that can propagate in the same fiber. And the relation between frequency and wave number, the relation between omega and K, are velocities. And therefore, the slopes of these diagrams represent velocities in which waves propagate. So I can draw here, for instance, the pump wave going in one direction with a certain frequency omega and a certain wave number K. And I can draw the signal wave propagating along the same mode in the opposite direction with a certain omega and a certain K. Now, if we can manage the stimulation of an acoustic wave, the process has to maintain energy and it has to maintain momentum. Now, how is this related? We identify energy with frequency and we identify momentum with wave number. Therefore, any acoustic wave has to connect between these vectors of optical waves, pump and signal, and it must also comply with the dispersion relation you see here for an acoustic mode. Let me make this maybe a little bit more concrete and explicit. The acoustic waves propagate with velocity v. The optical waves propagate with speed of light, velocity c over n. So let us see how this is related. The acoustic wave has to comply with omega over q equals v. But we already know what is q. Q is twice the wave number of the optical wave. So acoustic velocity is omega over 2kp. But we know more than that. We know that the optical wave number kp is related to optical frequency and speed of light, c over n. So if we compare the beginning and the end statement here, what we find is that the acoustic velocity determines which frequency exactly we're going to use here. This relation is only met for a very specific acoustic frequency. We call that the Brillon shift, or the Brillon frequency shift omega b. If we choose that acoustic frequency to be this exact value, then we comply with the dispersion relation that you see here. Okay, and I hope this is at least somehow understood. So when we're sending these two optical waves, we can hope to generate an acoustic wave of this particular frequency. This means that we have to choose the difference between omega pump and omega signal to equal exactly that. So we've defined the Brillon frequency shift, BFS, and In standard optical fibers, if we plug in the speed of sound in silica and refractive index and optical frequencies that correspond to a telecommunication wavelength, we expect frequencies on the order of 11 gigahertz, maybe a little bit less. And how is this related to sensing? Because the exact value of the Brillon shift is changing with temperature. Why? Because the speed of sound is changing. So if we modify temperature by 1 degree Kelvin, this value of omega B will vary by 1 megahertz. This might be not a lot compared to a baseline of 11 gigahertz, but nevertheless, this is measurable. If we identify such a change, then we can retrieve the ambient temperature. Similarly, this frequency is also changing with elastic strain or relative elongation of the fiber. If we stretch the fiber by 20 parts per million, what is called 20 microstrain, we also vary the Brillon shift by some 1 megahertz. So if we can somehow perform measurements of this value, omega B, if we can somehow devise setups to monitor this stimulation of acoustic waves, we can learn something potentially about temperature or about strain. So backwards SBS serves in the sensing of both quantities. And this brings up another question. How are we able to read out acoustic waves? Obviously, we're only using light directly. In none of these setups, we're using like ultrasound probe or anything of the sorts. We're only sending light waves in and out. So there has to be a way to deduce the presence of these acoustic waves via light. And here we rely on an effect that's called photoelasticity. When we have an acoustic wave in a fiber, this means that density of the matter is fluctuating. This perturbation, this is accompanied hand in hand with perturbations to the refractive index. So if density changes, index changes. So if this is my fiber, for instance, and we have this acoustic wave stimulated, what happens in essence is a disturbance in refractive index that is in itself going along the fiber. The acoustic wave is periodic with regions of higher and lower density alternating. This is also suggesting that the refractive index will be higher and lower alternatingly. So in essence, what we end up with is a grating, a periodic perturbation in the index of our optical fibers. And what gratings do is scatter light. Therefore, once this acoustic grating, if you will, exists in a fiber, part of the light in this fiber will be affected, will be reflected and scattered away. And this is how we make measurements in Brillon sensors. There is, however, one important distinction between normal gratings and these acoustic waves is that acoustic waves move. They have a velocity, the speed of sound. Therefore, any reflection from these acoustic waves will be shifted, will be Doppler shifted in frequency. This is not a simple linear reflection. Okay, so we monitor photoelastic scattering. This is what we do. And we can distinguish between two strategies for doing that: spontaneous versus stimulated scattering. And what do I mean by that? In spontaneous scattering, we forget for the moment about our pump and signal and send another independent optical wave. We call that a probe for the purpose of monitoring only. So that probe is not driving the acoustic wave to begin with. All it does is read them out and monitor them. And so these could be acoustic waves that were stimulated by a pump and a signal. Sometimes these are acoustic waves that exist irrespective of optics. We do so, and the probe light we're using is not generating them, it is only reading them out. In stimulated scattering, on the other hand, we observe the effect of the acoustic wave on the same pump and signal that brought it to life in the first place. So there's some kind of a feedback here. It's the pump and signal that make the acoustic wave happen in the first place, and the acoustic wave in turn is modifying the exact same waves. And this is what we're going to look at. And both protocols are being used towards sensing, but in what we speak of today, I will dedicate most of the attention to stimulated scattering. So in the case of backwards SBS, part of the pump wave, part of the pump magnitude is backscatter by the traveling grating. And backscatter means that it is joining in the direction of the signal. And because of the Doppler shift, that scattered component is now assuming the wave number of the signal, and it is assuming the frequency of the signal, which means that we've added part of the optical pump wave in the signal, to the signal, and made it larger. So all in all, the scattering process is amplifying the signal wave at the expense of the pump. Part of the pump wave, is being added to the signal. And in many of the protocols we use in sensing, this is exactly what we observe. We'll send pump and send signal, and we'll look for amplification. We'll look to see if there's any gain imposed on the signal. If there is such a gain, this is a sign for us that a stimulated Brillon scattering process had taken place. And if we look at this process carefully enough, we can achieve sensing of either temperature or strain. So a bit of an interim summary, maybe 1/3 of the way into this presentation. What do we know about the process? It is driven by two counter-propagating optical waves, one in the positive z direction, one in the negative z direction. It is generating acoustic waves that are longitudinal. They themselves propagate along the axis of the fiber. All the three waves involved, optical pump, optical signal, and acoustic wave, are all confined to the inner core of the fiber, which means we do not access the outside of the fiber in any other way, and I will revisit that property later on. The typical acoustic frequency we're speaking of is 11 gigahertz, and that frequency is sensitive to variations in temperature and strain. Now what? So suppose we can measure such signal gain. The gain will accumulate over the entire length of the fiber that we're testing. This can be meters, hundreds of meters, kilometers, tens of kilometers, and this is all very nice, but in many sensors, we actually look to map out quantities as a function of position. We want to distinguish between one region and another. We want to identify perhaps the temperature is higher in point A than in point B, that strain is larger in point A than in point B. And in our community, we refer to such measurements as spatially distributed. So we look to map out a quantity of interest in a continuous manner as a function of position, and as opposed to just a single readout. And to that end, we must learn how to resolve the Brillon gain information from one position to another. The most common protocol to do this is based on time domain analysis. This is why it is called Brillon optical time domain analysis, or BOTDA. And in these protocols, typically, we launch a signal wave that is continuous, and we send a pump pulse in the opposite direction. And these two waves, a continuous signal and a pump pulse, interact. And they interact in each and every fiber position over which this pump pulse is propagating. Now, in every point, this interaction depends on the agreement between the Brillouin shift and the difference omega that we chose for this pump and signal. If there is agreement, there will be gain. If there is lack of agreement, there will be lesser gain or no gain at all. And this is something we can observe and resolve. For instance, let us envision a piece of fiber like this, where there is a different omega Brillouin in this central red region, and we'll be sending a signal in a pump with a certain difference omega between the two, but we choose it so that the difference matches omega Brillouin in this dissimilar region, but the difference between frequencies omega is not in agreement with the Brillouin shift anywhere else. So a pulse of the pump wave will cut across like that, and our signal, well, there will be no amplification here because the difference omega does not match the Brillouin shift. Then there will be a limited region of amplification because only here there is agreement between acoustic frequency and Brillouin shift, and then again, there will be no further gain. So the signal power that we will measure will exhibit a rather short event of amplification, which would correspond to the extent of this region that I denoted here in red. And this trace that we gather, that we collect on an oscilloscope, shows signal gain as a function of time. However, we can relate time and position very simply based on the speed of light. Therefore, what we achieve, in essence, is a map of signal gain as a function of position. So we may now, if we want to gather more information, we can change that omega, we can change the difference between optical frequencies of pump and signal, repeat the experiment, maybe get a different trace, or probably get a different trace, and when we analyze a collection of such traces, we end up with more complete information regarding the SBS processes in each and every position along the fiber. In the end of the day, we end up with maps like this. And this map is taken from a paper by the group of Professor Moshe Tur in Tel Aviv University. Moshe has been my master's advisors in the 90s, but continues to be my mentor for life for many things academia and beyond academia. And what you see here is a map of Brillouin gain in colors as a function of position. This is position in meters, and this is frequencies. So how a map like this is collected, that we set the difference in optical frequencies between pump and signal, say 10.9 gigahertz, and we cut across, and we observe regions of gain and regions of lesser gain, and so on and so forth. And then we modify the difference to a different value, say 10.85 or 10.8, and gather such traces one after the other, and combine them all to get a 3D map like this. And when we do that, we observe that certain regions of fiber, such as this, are characterized by a Brillouin shift of 10.9 gigahertz, whereas maybe other regions are characterized by a higher frequency. So this region is different from the others, perhaps in temperatures, perhaps in strain. For the moment, we do not know. But these are the sorts of maps that we're collecting in backwards SBS sensors. Now, if we were to cut across, maybe I'll do it here first. If we were to cut across in a given position and note the gain is a function of frequency in each and every one of these positions, what we will get is a curve like this. This will be the local Brillouin gain spectrum. And it has a Lorentzian line shape, as you can see here, given formally by this expression. So it has a peak gain G0. That peak gain is achieved when omega matches omega Brillouin. This is when the denominator here is minimal. And the line width of these spectra is called the Brillon line width, is on the order of 30 megahertz. So in each and every position of fiber, we'll be collecting a Lorentzian spectrum such as this. But if temperature changes, from here it's minus 25 degrees C, 30 degrees C, 90 degrees C, what you'll find is an offset. Because omega Brillon changes with temperature, these spectra will move. Their line widths might change somewhat in this example, but when we identify the peak frequency, then we've learned something about temperature and or about strain. Now, I showed you the spectrum in a one position, and when all said and done, we can draw the frequency of maximum gain, the Brillon shift, as a function of position. In this example, it is drawn over 50 kilometers, and this gives us a map of Brillon shift in gigahertz as a function of position. This particular example is taken from the group of my friend, Professor Alain Loaiza, in the Public University of Navarra in Spain. And I will try to give all the credit that is due to the people who actually did the experiments that I'm showing you. So the differences among the three curves are of less importance right now, but when each fitting here gives 1 point of Brillon frequency, and we do it again and again and again for each position, and we can identify regions that are maybe different from the others. You can also consider how much uncertainty there is. The sorts of noise we're getting in these curves, these sudden jumps represent, I suspect, measurement noise rather than true physical variations. So you can see that these are on a megahertz scale. And what does this mean? A megahertz error correlates or corresponds to a degree Kelvin, or 20 parts per million of elongation in the fiber. Okay, next, let us speak something about limitations, what we can and cannot do. And one thing we care about, of course, is spatial resolution. Can we distinguish between regions that are 10 meters long, or 1 meter, or centimeter, or millimeter? Of course, the higher the resolution, the better. We would rather distinguish between regions that are very, very short. But what would determine resolution? Well, it is limited fundamentally by lifetime. If we look at the gain spectra we've seen before, they have a width, a line width of a gamma Brillon on the order of 30 megahertz. But this line width carries an additional implications. The inverse of line width, tau, 1 over gamma Brillon, is lifetime. We need so many seconds to drive the acoustic waves. How many? Something like 5 nanoseconds. What does this mean? It means that the pump pulse must be long enough in order to effectively drive the acoustic wave. It has to be at least 5, maybe 10 nanoseconds long in place. Otherwise, the stimulation of the acoustic wave is partial and our measurements are degraded. Now, what does 5 nanoseconds mean? If you think about the speed of light in a fiber, then by the time 5 nanoseconds had gone, our pump pulse had already covered about 1 meter. And this is setting a very fundamental limitation on spatial resolution. It means it will be difficult for us to resolve features or resolve temperature variations or strain variations that are shorter than 1 meter. Because in order to see them in a naive way, at least, we will need a very short pulse, shorter than 5 nanoseconds. And if that pulse is indeed that short, then the entire process of SBS is not kicking in a very effective manner. So this is why, if we at least speak of traditional Brillon analysis, it is limited to the scale of something like 1 meter. Nevertheless, our community has not given up on spatial resolution. And there are literally dozens of very clever schemes that people devised in order to achieve much better resolution than 1 meter. I'll show you just one example. This example is a collaboration between the Harbin Institute of Technology in China and the University of Ottawa in Canada. And the lead author is Professor Yongkan Dong. And what he did is a very clever trick. He did 2 experiments. What you see here in black and red. The first experiment used a pulse that was 8 nanoseconds long. That is the black curve. And 8 nanoseconds is perfectly fine. It is longer than the lifetime. And then he did a second experiment. And the second experiment used a slightly longer pulse, 8.2 nanoseconds, which is also a valid experiment. And what he did next is subtract between these 2 traces. And the difference between gain red and gain black is exactly the addition or the extra that happens in the final 0.2 nanoseconds or 200 picoseconds. And this is very neat because if we were to try naively a pulse with just 200 picosecond duration, we'll be in trouble because this duration is not nearly long enough to generate acoustic waves. But in a subtraction like that, we're able to gain access, quote unquote, to the final 200 picoseconds after the entire stimulation of the acoustic wave already happened. And look, this is how they could resolve very fine features in temperature. What you see here is a map, again, of position, frequency, and gain in colors. And this is towards the very end of a 2 kilometer long fiber. And what you see here, the entire map here is a meter. And they've heated up a section that is only 2 centimeters, if I recall, of width, and they can see it. They can see it in the subtraction of the traces. And indeed, if you take the cross-section in each of these positions, like I've shown before, you can resolve a different temperature, which only prevails in very few centimeters. And this is much, much shorter than what you would naively expect if you just consider lifetimes. So this particular technique came to be known as double pulse pair acquisition. And I guess the name is now self-explanatory. And again, it is only one of many very neat and clever schemes people devised. And this just goes to show that we are not settling for just the 1 meter resolution as a community. So we spoke of resolution. What about range? How far can we get? And what is limiting us fundamentally is losses. Fibers are very transparent. They only lose 4.5% of the power, or 0.2 dB per every kilometer. But still, if you accumulate 100 kilometers, then 99% of the light is gone. And in order to compensate for these losses, one needs to launch in pump power levels that become stronger and stronger, but there is a limit to that. If we attempt to launch pump powers beyond reason, then competing nonlinear optical effects kick in and eventually restrict our measurements. Also, the optical power of our signal wave in the opposite direction is limited. If the signal is too large, then its amplification would eventually eat away the entire power of the pump, and this is not very advisable. So therefore, again, if we look at a standard scheme, it is limited to few tens of kilometers, maybe 30, maybe 40, maybe 50. It is not easy to go beyond that. But here too, we again, in the broad sense of the term, the community had not given up. And we were using all sorts of amplification schemes to overcome the limitations of losses and the limitations of nonlinearities. One example, this is from the group of Professor Luc Thévenin in EPFL, Switzerland. He used optical amplifiers every 60 kilometers or so. You can see the scheme here. So there are sections of fiber, 65 kilometers each, again and again and again. And in between these fibers, he's amplifying light. with lumped amplifiers, erbium-doped fiber amplifiers. And in doing so, he was able to recover the intensity of the pump in signal waves and compensate for the losses that accumulate along this fiber section beforehand. And what you see here, that he was able to measure the Brillon shift over 325 kilometers. So you see here, these are already the fitted peak frequencies, the Brillon shifts. They measure in the 10.8 gigahertz range, all the way over 325 kilometers. So this is one way you could do it. Another example is, rather than use lumped amplifiers at the end of a section, one can turn the entire measurement fiber into an amplifier. This is based on the principles of Raman gain. I will not go into details, but using the benefits of stimulated Raman scattering, the lossy fiber can become an amplifying fiber. So it's the same piece of fiber in which we're taking measurements, but we compensate for losses as we go along. And this particular example, this is by the group of Professor Miguel Gonzalez Herraiz from University of Alcalá. This is near Madrid in Spain. And he's showing here how he could measure Brillon gain over 100 kilometers of fiber that is comparatively uniform. I just want to draw your attention to this. The changes in gain that he's seeing between the best locations and the worst locations is on the order of a factor of 6. If I want to put this in perspective, in a naive fiber that is 100 kilometers low, there will be a drop by a factor of 100. So if you go start to finish over 100 kilometers of fiber, the gain will drop, not by a factor of 6, but by a factor of 100, which will, of course, will kill the measurement. So using Raman gain, Miguel and his team could measure these Brillon maps like I showed you before, position, frequency, gain, of well over 100 kilometers, and also resolve very narrow features here. This is about 75 kilometers from the input end, and this measures in maybe on the meter scale, and you can still see it. So range is being pushed towards 100, 200, maybe even more kilometers. What about accuracy? When we measure temperature, when we measure strain, when we measure Brillon frequency shift, in essence, just how precise is it? So this has to do, like many things in engineering, with signal to noise ratios. The better the SNR, the more precise is the measurement. And the same group at EPFL, this is Luc Temena and Marcelo Soto, who is now himself professor in Valparaiso in Chile, they devised a relation between the SNR and the accuracy of the measurement. Sigma B here is the standard deviation or the experimental error uncertainty in the Brillon shift. The better the SNR, the smaller the error. And it is also given by our frequency steps. Delta is the increment between the omegas we're using. So we gather data in one frequency and another, and another, and another in small steps. Delta, the smaller the steps, the better off we're going to be. And this simple relation predicts what is the SNR we need and what is the step in frequency that we need in order to reach a target experimental uncertainty. What do we typically get? Again, 1 megahertz uncertainty is a benchmark for good works. We can do better, sometimes we do worse, and it's all a question of SNR. And the derivations can be found in this paper. One last metric, we've spoken of resolution, range, okay, we've spoken about accuracy, but how long does it take to gather data? Of course, if it's very fast, then we're better off. We might even track dynamic behaviors, such as sound or vibration. On the other hand, if the acquisition duration is very long, many minutes, maybe even hours, then maybe the practicality of the scheme should be put in question. And the duration of the experiment is limited by three things. It is limited, first of all, by the time of flight, right? The pulse has to go into the fiber and the reflection has to come back. So the two-way time of flight along the fiber is a limiting factor, but fortunately, this is typically not a very strict limitation. If we're looking at tens of kilometers, hundreds of kilometers, we're still speaking of much less than a millisecond. So this is a fundamental limit, but it is seldom the only limit. On top of that, we must recall that we're scanning over omegas. Like I've showed you here, we have to take one omega and another and another and another. So experiments are repeated over typically tens of omegas. But that's not even the end of it. We must acquire a minimum SNR in order to achieve the precision that we're after. And the way to get SNR is to repeat acquisitions. One pulse and another, and 10, and 100, and 1,000, and average out all these traces and hopefully eliminate the noise and improve the SNR. So it's time of flight multiplied by how many frequencies and multiplied again by how many averages, and all these multiplications are adding up. One way to battle this is to maybe do away with the scanning of omegas. What if we could get the same information, or at least close to that, without scanning over omegas? And these techniques are called slope-assisted measurements. And here I refer to the tour group of Tel Aviv once again. I draw your attention to these three traces. The black one is called the nominal. So we'll adjust the difference, omega, between pump and signal, not to the Brillon shift, but somewhat to the side. We'll deliberately choose the difference where the gain curve is at a maximal slope. So now, if our Brillon shift is moving to the left, what we observe is larger gain at this single frequency. If the Brillon shift is moving to the right, what we'll find is a lesser gain. So, at least in principle, we do not need to scan the entire collection of frequencies. We do not need to retrieve the entire shape of this Brillon gain curve. All we need is monitor intensity. If there is all of a sudden more gain, okay, we know we traveled left. If there is all of a sudden lesser gain, this is a sure signal we've traveled to the right, and the scan of omegas is not needed. And this is one example where the tour group actually tracked a flexural wave going along a strip of composite material as it was happening in a matter of sub-second. You see here, these are entire gain maps as a function of position over 6 meters of fiber, as a function of time measured way better than a second scale, and you can capture a dynamics of a flexural wave propagating along this strip of composite using a very, very fast Brillon acquisition. And this can actually be extended towards kilohertz rates of mapping out fibers using slope assistance. Okay, so we're almost through here. I just want to show you one more paradigm of how you can achieve high resolution without short pulses. And this is called correlation domain analysis. Let me explain to you how this works. If you recall from the beginning of my presentation, the driving force for the acoustic wave stimulation comes from optical beating. It is the optical intensity that exerts a mechanical force, and the optical intensity is a beating between two waves. So in any set position, Z, and in any instance, T, the magnitude of the force is this inner product between pump and signal. But how much acoustic waves are we actually getting? In order to calculate this, we have to integrate over this driving force along a certain time. Rho is the magnitude of acoustic wave, and it is proportional to this inner product integrated over the lifetime. And this, to me at least, somewhat resembles the charging of a capacitor. There is voltage on a capacitor, but the charge we accumulate goes with the integral over this voltage. So now we can distinguish between two cases. If, on the one hand, if this product is constant, a fixed number for the entire duration tau, then we're able to accumulate the stimulation of acoustic waves. This would be analogous to the charging of a capacitor with DC voltage. And our experience tells us that you can charge a capacitor with DC voltage. So a constant product here gives effective stimulation. But what if instead this inner product is oscillating very quickly? What if this product is changing sign many, many times within the integral duration tau? In that case, the stimulation of the acoustic wave will be largely canceled away. And to continue on the analogy, it is like you were to charge a capacitor with AC voltage. AC voltage that is faster than the lifetime of the capacitor. So if the time constant, if the inner product is constant over the time product, there is effective buildup. But if it is changing too quickly, the acoustic wave is inhibited. It does not start. And we make use of this property in what came to be known Brillouin optical correlation domain analysis, or BOCDA. We draw the pump and the signal from the same source. So the pump is propagating in one direction. So in every moment, it is the input delayed. The signal wave is the same input from the other side, and it is also delayed. So we launch this one from z equals 0. So it is delayed by z over v. And we launch the signal wave, it's the same waveform from the opposite end, capital L, so it is delayed by L minus z. And now these two meet up. And the magnitude of the acoustic wave, therefore, goes with the inner product of the input waveform and itself delayed. And this relation that you see here is very much resembling a correlation operation. And if I were to spell it out, the magnitude of the acoustic wave is very closely related to the correlation of our incident waveform. If the delay here is shorter than the correlation length, very good. We can drive an acoustic wave. However, if this difference here, if this time lag here is longer than the correlation length, then the acoustic wave will be inhibited. So we can define a relative delay, this L minus twice Z over velocity or group velocity of light, and this is the argument of the correlation here. And the acoustic wave stimulation is effective only within a correlation peak, which measures like the correlation length of our source. This principle was proposed first by Professor Hotate from University of Tokyo in year 2000. And what I show you here is a variant that we extended in 2012 in my group with collaboration with EPFL. So we're modulating the pump and signal with a phase code. So the pump that goes in one direction is a series of plus and minuses alternatingly. And we're launching the signal wave from the opposite end with the same sequence in reverse. So when we are dead at center, what we find is always minus meets minus, plus meets plus. The inner product is stationary. Consequently, acoustic wave is building up. In any other position, to the right or to the left, what we end up with is, okay, sometimes plus meeting minus, sometimes minus meets plus. So this inner product is alternating. It will alternate very quickly. So the acoustic wave is largely inhibited. And if you were to calculate this, what I'm showing you is the magnitude of the acoustic wave as a function of position and time. And you can see it shows better on the panel to the right, that the stimulation becomes confined to a very, very short segment and stationary within that segment and largely inhibited everywhere else. And if we carefully retime the modulation of pump and signal, we can scan this position of acoustic wave stimulation from one region to the next and achieve a spatially distributed mapping. And this principle was scaled to hundreds of thousands and even millions of resolution points. This is an example from my group in 2014, where we reached 80,000 points, 2 kilometer range, 1.6 kilometer range, 2 centimeter resolution. Here again from my group several years after, when we've reached almost 10 kilometers with the same spatial resolution, that's almost 500,000 points. And in the same year, the group in EPFL reached almost 2 million points. That's close to 20 kilometers of range with 8 millimeters of spatial resolution. Okay, I'm going to skip this and just tell you that these principles are not just a lab curiosity. There are several companies that are commercializing the principles of Beryllion sensors. I've picked just one. This is Omnisense from Switzerland. I have no particular interest in this company. It is not a single one, but it just gives you beautiful illustrations of how they install fibers in pipelines, in power cables, in undersea infrastructures, in bridges, and so on, and gather critical information about the well-being of these essential structures, and hopefully detect potential flaws in an early stage. Okay, I will do the second part of this talk very, very fast. So actually, this has been longer than I anticipated. So I want to spend just 5 minutes on what we can do in the forward direction. And I want to introduce this part with a dilemma. And what you see here, I believe, will be familiar to many of you. And everything the light touches is our kingdom. This is something we all like to say. But this statement in optical fiber sensor is not a good thing, it's a bad thing. Because in order to take a measurement, light has to touch on the things that we measure. And in standard fiber, since light is confined to the inner core, we're not touching anything. Light is here. And many times the things we like to measure lie outside a cladding that is much, much, much larger, so we have no touch with them. So I can measure temperature in Beryllion sensors because temperature prevails in the core. And I can measure elongation or strain because axial strain prevails in the core. But if instead we wish to measure a medium that is beyond the cladding, we cannot do it because light is here. Also, in the Beryllion sensors that I told you about in the main part of this presentation, they are not helpful because the acoustic waves are also here. And we have no handle on what is happening outside. But this can also be corrected. And I'll do this very fast. I'm going to skip all this for the sake of time and just tell you that optical fibers also support elastic waves that span the entire cladding. In these modes, the material displacement, the elastic waves, is not axial along the fiber, it is transverse or even purely radial in the examples I'm showing you here. And unlike optical modes, you can see here that the elastic waves in this case span the entire cross-section of the cladding and they reach the boundary. And there is a set of modes like this. Again, I'm going to skip for the sake of time and just come to the essence of it. I want to illustrate what happens when I'm sending a pulse of light down a fiber. I'll play this one in the left first. So I'm sending a short pulse of light into a cross-section of the fiber. And this pulse of light was short, it came and went, but it leaves behind an elastic disturbance. It is stimulating a packet of these transverse acoustic modes that I showed you before, and this packet is propagating, I'm going to play it again, is propagating from the core outwards towards the edge of the cladding. And when it is hitting on the cladding, like now, there is an elastic reflection. So every so many nanoseconds, 21 nanoseconds to be exact, the elastic disturbance is being reformed within the core. In this calculation, I assume there is vacuum outside the cladding. Therefore, the elastic reflection now is perfect. And every echo that we get, like now, will be just as strong as the one before. But this is only because I assume there's nothing outside. If instead we assume now there is water outside the cladding, now there is partial transmission, and part of the acoustic energy is dissipated away. Therefore, the next impulse now is actually weaker than the one before. And the third impulse will be weaker still. And if we were to monitor, I'm just going to show this one more time. If we monitor these decay processes, if we monitor these decay rates, we should be able to conclude what is outside. If the elastic properties outside the fiber are in better agreement with the fiber itself, there will be larger dissipation, there will be faster decay, and so on. To quantify this, we can predict the decay rate as a function of mechanical impedance, as a function of the properties of the outside medium. This will be so many megahertz if we place ethanol or water or polyimide outside. And there is a very simple formula that will connect between the decay rates and the impedances of silica and outside medium. Of course, the impedance of silica is known. Therefore, when we measure the rate, and this is speed of sound, and this is just radius, then we know, based on mapping like this, what is outside. And those of you who are familiar with optical cavities will recognize that the exact same relations hold with optical cavities, with optical transmission and reflection. It's the exact same principle, only these are not electromagnetic impedances, these are elastic impedances, but everything else that we know and love is completely relevant. Therefore, and I'm again going to skip, we can use these elastic echoes in the cross sections to make sensors. I'll now go to experiments. This is the first measurement that my student Yair Antman took some 4 years ago. And in this experiment, the fiber with no coating, kept in air, and we could actually observe in the lab these successive impulses with intervals of 21 nanoseconds, just like one would expect. And this series of impulses is rather extended. It is lasting almost a microsecond, which is eternity. And the reason is there's nothing outside the cladding or just air outside the cladding, so there's very little dissipation of acoustic energy. And if we were to repeat the same process with ethanol or water outside the bare fiber, what you'd see is a much faster decay. It's no longer a microsecond, it is decaying over 100, maybe 200 nanoseconds, and you can already see fine differences between ethanol and water. And if we were to select just a single of these acoustic modes via post-processing, then you see there is exponential decay, and it is faster in water, and it is slower in ethanol because of the difference in impedances. And this agrees quantitatively. If we calculate the mechanical impedance based on our data, we find values that are very, very close to literature values. Literature values are this dashed line at the back, and we'll repeat the experiment for different modes, and we get different readings. We do it for water, we do it for ethanol, and the agreement is within 1%. And this was kind of nice because for the first time, you could get a measurement of what is outside the fiber, even though light never gets there. And of course, we do this indirectly. We do this via the acoustic waves. The acoustic waves are serving as our messengers. And we use light to drive them, we use light to monitor them, and indirectly get a handle of what is outside. And this technique is actually good enough to resolve different aqueous solutions with different levels of salinity, DI water, 4%, 8%, 12%. This is something one can resolve. And I leave you with just one last measurement. I told you we like distributed maps, so we could do that in the case of measurements outside the fiber as well. These are maps of position again, frequency, and Brillouin gain. In this case, frequency is much lower. It is the frequency of these transverse optical waves, so 320 megahertz. And you see here 3 kilometers of fiber, which is coated for the most part, but the coating was taken off 100 meters towards the output end. So in this position only, all of a sudden we're seeing a much, much stronger interaction and much more narrow spectrally, because the decay rate is so much slower when there's no coating. But if we were to immerse that bare section in water, then all of a sudden this washes away. And there is a much broader and weaker peak than before. And if we put it in ethanol, there's maybe something in between. And we get these spectra that become wider and wider as we move from air to ethanol to water to coating. And even though they're all fitted by Lorentzians, the width is very, very different. And we can get decay rates as a function of position, where you can actually see the difference between air, alcohol, and water outside the bare section, whereas these decay rates remain constant in all the previous parts that are just coated and not exposed to liquids, and they are the same among the measurements. Okay, I'll skip this final part about coatings, and I just really want to thank my team here of current and former students, Dr. Yair Antman, who is now in the Corona capital of the world in Manhattan doing his postdoc, Yosef London, who recently submitted his PhD in my group. Chagai and Gil are excellent current students. Chagai is awarded the Azrieli Fellowship for his PhD studies, and Gil just received now his fellowship from the Adams program. Dr. Eyal Preter, now in Magic Leap up north, and Dr. Arik Bergman, he's a current postdoc in my group, completed his PhD with Moshe Tur in Tel Aviv, and has been with me for several years now. And this is us together in a conference last year. We hosted a conference when conferences still existed, and this is everyone who attended. And I really thank you for your attention and for your time and participation in this webinar. So I'm seeing here a couple of open questions. One of them is asking if will the video be available for streaming later on. I believe so, and I think this is a question to AEAI, the organizers. To the best of my knowledge, this is being recorded and will be available. At least I'm in favor of that. And the second question has been, can you show a sketch of the simple setup for these experiments? I missed the first slide, so sorry for this question. Yes, okay, you did not miss because I did not show. There was enough of a technical detail and length as it was. And if you want to contact me by email, I will be very glad to share setups and papers and all the details. I do not have it as part of this presentation due to an excessive amount of detail and information. If there are any more questions, then please feel welcome to address them via the Q&A interface of the platform. And if not, then you can always contact me via email, and I'll be very glad to share these presentations or anything else with you. Okay, now in the chat, you can see that everything was being recorded and will be uploaded. So thank you, Roy, for that. So in case there's nothing further, I want to wish all of you good holidays and be safe and well and healthy. And I hope that we return to normal seminars and normal conferences as soon as possible. I'll stop the sharing now, and goodbye, everyone.